also, if you have learned something about numerical analysis courses, and you may remind that there is a very famous interpolation algorithm called Lagrange interpolation algorithm. And the mathematical form of the algorithm is like this, where xi's and yi's are sample points. X is the point we want to interpolate, and this is the result. And this algorithm can be programmed under Matlab like this. And you can call the function to perform Lagrange interpolation. And there is a countervailing example for that kind of interpolation. Suppose the original function is something like this. We can generate data from this function using the commands like this. And then we can perform Lagrange interpolation from the data. And let's see what are the results. In the results, the solid ones are the original or theoretical data. The solid line are from the theoretical curve or theoretical function we obtained. And these points are sample points. And the dotted line are from Lagrange interpolation. So at some parts the interpolation result is not quite good. So for this example, we better use the one provided by Matlab like this. Inter P1, X0, Y0 are the given data sets, and X are the interpolated data, and then we can use the line option. Then we can display the interpolation result. And it can be seen that the result is quite close to the theoretical one.
How can you know which one is better than the one?
There's no way to check it. Sorry, I do not think there is a way to check it. The best way, I think you can the best way is to select different measures and draw them out and see from the results itself, maybe, which one is smoother. Okay, so this is a demonstration of one-dimensional interpolation. So let's consider two-dimensional interpolation problems. On this part, I will explain for two cases. Case 1 and case 2. Case 1 is for the data, for the problem where the original data sets are given as a grid, in grid, the data are given in grid. So for these points, the data are given. The other case is a generalized case where the data may be distributed in a random way or in other irregular ways. So there are two cases. One is for two-dimensional interpolation with grid data. And here is the command we should use where X0, Y0, and Z0 are the sample points which are given in grid data. And X1 and X2, X1 and Y1 are the data for the points which you want to interpolate. And again, that's the method. And again, I should assume that we better use the option line. And by calling this function, we can find the interpolation value of C1 from it. And this is a function to use. Here we should generate a set of data using command like this from the given function. We can generate a set of data like this. We can use mesh query to generate the grid data, and then we can use this function to evaluate the given function. And we can draw the surface from the sample data. And these are the sample data, the plot of Chen by using the sample data. And it can be seen that these points may not be very accurate if we just use linear interpolations. So now we can generate another set of data with smaller spacing between the points. It is again mesh grid data, because we want to draw three-dimensional curves, the three-dimensional surfaces. And the option here is better use spline. And these results are smoother at certain points. And in Matlab, if you do not want to use the interpolation point, you can also get a smoother surface using commands. For instance, you can use shading inter-P, which is done actually under using the interpolation method, but you do not have to use it in an explicit way. You can get results like this. But you cannot get the data from it. You can use this command to get a smoother surface. And you can, because the theoretical function is known, you can compare the results and find the error, and show the error surface.